Okay, hey guys, it's Rachel Reed here, and you are currently watching my A Year in Review project. And pretty much in this project, I'm just going to be talking about some of the things I learned this year in math, about myself, and just some of the stuff we went over. So that's pretty much it for this slide. Thank you for watching, and this is my project. So to kick off my project, I have to talk about one thing I learned in mathematics about myself. So that's what I'm going to be doing. Okay, so what I feel that I really learned about myself this year in math is that I can do math and I can understand math really well if I just sit down and I take each of the formulas we're using and each of the problems we're working out, and I break them apart piece by piece into their simplest components, and I really look at them that way. Um, Going through that process this year has really helped me sort of improve as a student, because if I break it down the way that I've been doing, I can sort of see where I make potential mistakes, and I can see how certain properties work in math, which really helps on some of the tests um, or quizzes, where if I see a math problem that I find foreign to me, I can still break it down into steps and work through it. Um, and I've always sort of struggled with math. I've never been particularly good at it. And I struggled with it in elementary school and middle school and at the beginning of high school. But this year, math sort of just clicked into place for me, and I was able to sort of get what we were doing in class, and when I broke things down the way that I'm doing now, I could really sort of grasp mathematical concepts and really understand, and that allowed me to be a part of sort of in-room mathematical discussions and really like get how we were going from one step to the other, which was actually a really great improvement for me this year. Um, so yeah, pretty much I just learned that for me to learn math, I have to break it down into simple components first. But once I do that, it's really easy, and I have it pretty much after that. So now to continue with my math project, one mathematical concept I won't ever forget, and why. So one thing I learned this year that I will never, ever, ever forget. Okay, so the mathematical concept that I picked that I don't think I'll ever forget is the unit circle. Um, and I pretty much picked the unit circle just because it's the basics, it's the fundamental part of trigonometry, and it involves so many different things. Um, it involves the conversion from radians to degrees, um, and from degrees to radians, and the different sort of quadrants, and finding the exact values of certain angles, which is a very important part of trigonometry and will probably still be involved in calculus next year. And just because it involves so many different things, I feel as though we're going to be I feel as though we're going to be using it a lot, and we're going to be using it for a lot of different things, um, and it's going to be a part of a lot of different things. And just because of like constant exposure to the unit circle, I feel as though it's something that will be like ingrained in your memory, and you can't possibly forget it. Um, so really, the unit circle, it's the fundamental. So it's kind of like, I picture it as kind of being like addition and subtraction were in elementary school. We were exposed to addition and subtraction as the fundamentals of math, and now we've seen it so many times, it's just like second nature to us. We'll never forget how to add like 2 plus 2, or we'll never forget how to subtract um, 1 from 6. You'll never forget those concepts, and I don't think we'll ever forget the unit circle either as a concept, especially when we're going to be doing so many different things with it, and it's going to pop up a lot more next year. So that's pretty much why I picked the unit circle. Okay, so now I get to talk about the stuff I actually like doing. Um, and there were actually topics I like doing in math this year, which is like different than in previous years. So I'm gonna go on to that next. This is just the transition. Okay, so one topic I really love doing this year was sum and difference formulas. And I don't actually know why. Actually, I do think I know why I like doing them so much. Pretty much sum and difference formulas are just formulas you memorize them, and then you know them, and you know how to do them, because you just have to plug in numbers for sum and difference formulas, which is so easy. Um, and the only way you can do it wrong is if you forget it, but I had it memorized, so I would always get sum and difference formula. I would always get the answers to sum and difference formula questions correct, which was great. Um, so yeah, that's pretty much why I like it, just because I knew how to do it. So here's, I think we had to give an example of the concept that we liked, so I gave an example, and my example just has, I like superheroes, so my example has Batman in it, because Batman is cool and Batman rocks. Um, so here's my example. So okay, so let's say Batman needs a new chair for sitting in front of the Batcomputer. When designing the blueprints of the chair, he finds that two angles of the chair aren't adding up right. So Batman has to find the exact measurement. So yeah, instead of using the angles, he wants to find the exact measurement of the chair. So the first angle he needs is a 75-degree angle. So we all know that a 75-degree angle, finding the exact measurement would be hard because it's not listed on the unit circle anywhere. So how is he supposed to find the 75-degree angle if it's not on the unit circle? Oh no, what is Batman going to do? Well, he's going to use the sum and difference formulas. Um, so as you can see, he would take cos 75 degrees, and he would find two angles on the unit circle that actually add up to cos 75 degrees. And I chose 30 and 45 degrees here. So he would use the sum formula for 30 and 45 degrees. And he would just plug in 30 and 45 degrees into the sum formula to get cos 30 times cos 45 minus sine 30 times sine 45. And he would find the exact values of each of these angles for cos and sine, which for cos 30 is the square root of 3 over 2, cos 45 is the square root of 2 over 2, sine 30 is 1 half, or not 1 half, but a half, and sine 45 is the square root of 2 over 2. So then he would plug in those exact values into the place of cos 30 and cos 45 and sine 30 and sine 45, and he would ultimately end up getting square root of 6 over 4 minus square root of 2 over 4, which he can then combine those two together to get the square root of 6 minus the square root of 2 over 4. And that is how he would find the exact measurement of a 75-degree angle, because it's not in the unit circle. So now that I've done that, I'm going to move on to the real-world example, or the real-world application of sum and difference. Okay, so according to the research I did on sum and difference formulas, I found that there are no real-world applications for sum and difference formulas. However, they are still a very important part of calculus due to the fact that they are used to make certain problems easier and eliminate excess steps in some problems. When you get into higher level calculus, sum and difference formulas are um, often used to make certain problems less long and less complicated. And it's easier in calculus to graph the integral of a sum than the integral of a product. So while there is no real-world application that requires the use of sum and difference formulas, it's still really important to know what sum and or what the sum and difference formulas are, because it will make calculus easier in the future. And that's it. So, now we're going to talk about one topic I could definitely do without, math, that I really didn't like this year. I hated these problems. Just, I could never do them right. So, that's going to be next. Okay, so the problems that I could not stand this year because I couldn't get a hang of them are the trigonometric word problems. And you know what problems I'm talking about. These are those pesky little problems that had, like, where you define the linear velocity and the angular velocity and the arc length of stuff. And they would give you like word problems. They'd be like, a Ferris wheel is has a radius of this, and it has a central angle of this, and calculate the angular velocity and all this impossible stuff. And it was very confusing to me how to do these things. Um, I knew they were just simple like equations, but I couldn't remember the equations, and it was just it was really bad because I'd never get them right the first time through, and I would have to give them like a second try, um, which wasn't good on like your tests and our quizzes and things like that. So now I'm going to move on to an example of how to do these impossible problems next. So here's my example, and this one doesn't have superheroes in it, which makes me kind of sad. But it just has a Ferris wheel. Ferris wheels are cool, so I mean, I guess it's good enough. So pretty much, for my example, I'm saying, okay, so let's say someone is riding on a Ferris wheel, and they observe that it takes 30 seconds for a roller coaster to make a complete revolution. And the seats set at a and the seats set at sit at 30 feet from the axle of the wheel. What is the angular velocity of the wheel? So pretty much what you first need to do is start by trying to figure out what it is you actually need to solve this problem and what it is you don't need. And to find the angular velocity of something, you pretty much just have to know the amount of time it takes for one revolution to pass, or the amount of time it takes for a certain number of revolutions to pass in an object. So the information that you don't really need is how far away the seats sit from the axis of the wheel, so you can pretty much just mark that out. You're not going to use that. So once you know what you exactly need, which in this case is just how much time it takes for one revolution to occur, and we know that it takes 30 seconds to complete one revolution, as stated by the word problem. So what you're going to do is you're going to do one revolution over 30 seconds. And then you're going to multiply this by the number of minutes. So you want to find out the number of revolutions per minute, which is angular velocity. So you're going to multiply this by the number of seconds in a minute. So it's going to be one revolution over 30 seconds times 60 seconds over 1 minute, due to the fact that there are 60 seconds in a minute. And you pretty much end up getting 60 seconds over 60 over 30, which is equal to 6 over 3, which is equal to 2. So you have 2 RPMs, which is revolutions per minute. And that is the angular velocity of the wheel. So it makes 2 full revolutions per minute. And that's about it, pretty much. So now we're going to move on to the real world application. And this time, I'm not letting you down, because there's actually a real world application for angular velocity, which is also known as angular momentum. And sort of a real world application for angular momentum, or just things that have angular momentum. Um, and I have two separate sort of things. In football, you have angular momentum, and when a bullet is shot out of a gun, you have angular momentum, and this angular momentum is due to the added spiral of an object. In football, they want to throw the football. The quarterback wants to throw the football with a perfect spiral. And when you shoot a bullet out of a gun, there's actually ridges on the inside of the barrel that help to spin the bullet in mid-air. And the reason they do this is that the added angle of the object actually helps to stabilize the path of the object flying through the air. And due to this, you can actually calculate the angular velocity of a bullet and a football. And I think you can probably actually calculate it to see what angle or what angular velocity you get the best sort of stabilization in the air, which I think is pretty cool. Yeah, and that's pretty much about it. And I believe this is the end of my presentation, so thank you for watching, you guys. It was really awesome, and this project was really fun, so yeah.